So for a problem like this, where there's loading, how do you find the normal stress? This is the maximum normal stress, maximum shear stress due to shear force P, and maximum shear stress. Okay, so you start off with the shear force diagram. Before that, you need to find the reaction forces. So let's draw that beam again. Say there are forces like so. Okay, so let's find the reaction forces VA and VO. Now here H, or the horizontal reaction forces, are 0 because there's no reason to have them, because there's nothing resisting horizontal motion, right? So if you sum the forces in the y direction, you have V0 with a negative sign, VA with a positive sign, and this 1000 or 100, sorry, times the distance, this is 18, so times 8 should be equal to 0. So we have VA minus V0 equals 800. Okay, next, we can take moments about any point. Let's do it about O. So we have VA, the moment arm is 8. So VA times 8. And that moment arm is going to be counterclockwise. So I'll put a positive sign. And then we have 100 lbf inch. The net force due to that is times 8. The moment arm of this is going to be somewhere in the middle, right? It will be here, where this is 4. That is it. So the moment arm from O is going to be 12. And then this force, or this moment, is going to be clockwise. So I put a negative sign. So 0. So now we can solve for VA. It comes out to be 1200. And from 1, we can solve for V0. Comes out to be 400. Okay, but you expected to know how to find the reaction forces and shear force bending moment for the exams. Okay, so now we've got the reaction forces. Let's draw the shear force and bending moment diagram. That's going to be my shear force diagram. Okay, so let's start from the left and go to the right. We might as well replace these forces. So V0 was 400 and VA was 1200. So the shear force on the left side is 400 negative. So just try it. This is 400. and it remains the same all the way till we reach point A where it's upward. So we need to do 400 negative 400 plus 1200, which is 800. We go up. And then what happens here is that the net force here is going to be 1200, sorry, 800, right? Which is this, which is upwards. And we need to subtract out the one due to this load. So it's going to be 100. And if you take a small section like this, distance x, it's going to be x. And since the, sorry, so it's going to be 100 times x, right? That's the shear force. And x will change from, you can see if it'll be 0 all the way to 8. So clearly when you put x equals 0, the shear force is 800. And when you put x equals 8, you get 800 minus 800, that's 0. So all we need is 2 points to join it. So that's going to be how it will look. Okay, that's the equation. 800 minus 100x is the equation. Okay, so let's go and draw the bending moment diagram. Okay, so the one way to do this is to write the moment starting from left, and every time the shear force changes, you have a new equation and you can use that. But the other trick, which is probably simpler, is to find the area under the curve. So area under the shear force diagram here is going to be 400 times 8. That's the area of this rectangle. So it's 400 times 8, which is negative 3,200. And then this is going to be 800 for the height, 8 for the base, and then area of a rectangle.
Negative 600 come from?
It's 400. So height is 800, the base is 8. So that is half base times height. That'll also be 3,200. So what will happen is it will look something like this. It'll increase linearly. Okay. The reason why it increases linearly is because the moment here is going to be proportional to x, right? What's the moment? It's going to be 400 times, it'll be some formula, but it will be a linear function of x. And so it'll be a ramp like this. It won't be a horizontal line. From here to here, so this is 3,200. Now from left to right, it's clearly going to be 0 here. It's 3,200 there because, well, it's 0 there because 3,200 plus 3,200 ends up being 0. The question is, how do you connect the 2 points? In this case, because it's a distributed load, the moment comes out to be proportional to x square. The reason why it's x square is because when you take this element, you do shear force, which is 100x, times x divided by 2, right? That's where the moment will be. It's going to be force times the distance. So this is the force, that's the distance. So it's going to be somewhat like square. And so it's going to be a curve and not going to be a straight line. In fact, it'll actually look like this. Okay. The way you can do this is to write the equation and then do 1 or 2 points, and then you can join the curve. Okay, so that's my shear force diagram, the bending moment diagram. Okay, so now we need to solve for, go back, solve for maximum normal stress, maximum shear stress. So maximum normal stress due to M, maximum shear stress due to V. Okay, so we need to locate the point where M is max and locate the point where V is max. And that we can do from this diagram. You can see that V is max here and M is max here. Now, when I say max, well, you may argue that that's actually M min, right? It's minus 3,200. But the way this bending moment works is one part is going to be under tensile loading, one will be under compressive loaded. So even though one part is minus 3,200, there's a stress which is going to be compressive. The other part of the beam, which is if the top part is under compression, then the bottom part is going to be under tension. And so it's the magnitude which matters and not the sign there for M. Okay, so let's do part 1. Sigma max is M max. Y is going to be, well, in this case, we have a rectangular cross section. I think the dimensions are 1 by 2. So this is the height, this is the width. It's given to be 1 inch, 2 inch, and since the bending moment is in the plane, we'll see that neutral axis is this. Neutral axis. So this is Y. So the max is going to be, yeah, so it says that's negative, which means that the negative here means that it's going to be this direction, the moment. If the moment is in that direction, then you can see that the top layer is in the tension and the bottom layer is in compression. So the tension sigma max will be here. And I can write the sign. It's going to be, well, it's Y max. So it's going to be 2 divided by 1. That's the distance from the neutral axis, divided by the inertia, which is 1 divided by 12.
Is that 2 divided by 2?
Yeah. This way.
All right.
Hold on. Is the sign right? Let me check something. I'm trying to go back and see the sign convention I used for bending moment diagrams. Quickly check that. Okay, so if I go back and look at the sign convention, it says the following. So this is dividing the left from the right. M is positive. This way, M is the left, is the right. Okay, so if I have a negative sign here, it implies that this is this way. So yeah, I guess this is correct. It should be this way. And so then, so if this is acting that way in the direction I showed, then the top part is going to be under tension, right? So this is right. That's correct. 3,200 times 2 divided by 2 divided by 1 divided by 12. It's B times H cube. Okay, so B is 1, H is 2. Sigma max is we get 4,800 psi. Okay, next is find the maximum shear stress due to V. So V max is right there. Now the thing about shear stress is the maximum shear stress occurs in the middle. Okay, it doesn't occur on the edges. So the formula for maximum shear stress for a rectangular section is 3 divided by 2 the shear force divided by the cross-sectional area. So the shear force, which is the maximum shear force, is 800. The cross-sectional area is B times H, right? So B is 1, H is 2, and this comes out to be 600 psi. Okay, now the final question is asking us to find the maximum shear stress. Okay, so this is the maximum shear stress in the sense of the Mohr circle. So this stress is really sigma x. Agree, it's x in the x direction. This stress is really tau xy. And note the place where it acts. This one acts here. This one acts there. So in order to find the maximum shear stress, now we have two candidates. We can find the maximum shear stress at the top, maximum shear stress in the middle. So let's find the shear stress at both these points, and then the larger of the two value is going to be the maximum shear stress. So at the top, by top I mean this point, we have tau max equals square root Now at the top, we know that there's no shear force. There's only a sigma max, which is sigma x. And so I put sigma x equals 4,800 divided by 2, 0 plus 0 square. So we can see that tau max is 2,400. At the middle, which is now this point, you can write the same formula. Sigma x minus sigma y divided by 2 square plus tau xy square. So now I put the normal stresses are 0 there because it's on the neutral axis. So only the shear stress, which we computed to be 600 psi. So the maximum shear stress is 600. And so from, let's call that 1 and 2, this is the maximum shear stress. And it occurs at the top and not at the middle. Yeah, so that was the part which students in the second exam did poorly on. The other thing was single student who got this right. Okay, questions? Okay, so here's a question on finding the maximum normal stress. Okay, and the reason why it's kind of slightly different from a beam problem is because there's a change in geometry. So when there's a change in geometry, there's going to be a stress concentration, and you need to take into account stress concentration when you compute the maximum normal stress. So this is a problem where you'll see how the stress concentration affects our judgment of how to compute the location of the maximum normal stress. Okay, so part of it has the same flavor as the previous problem, where we need to first find the reaction forces, draw the shear force and bending moment diagram. In fact, we don't need the shear force diagram, we only need the bending moment diagram. Once you have the bending moment diagram, we can find the maximum normal stress from the maximum moment, and we'll solve it. So this is sort of the first part is exactly like the previous question. We compute the reaction forces and shear force and bending moment diagram. So let's do that first. So you're told that this is a bearing which is assumed to provide simple supports. So let's say R1, R2. This P acts at A, and A is a fourth of a meter, while the length is 1 meter. So this is 0.25. Like this is 1 meter. Okay, so Y X R1 plus R2 minus, I think P is given, it's 100. So let's put 100 equals 0. So that's my summation in the Y. And so that gives me R1 plus R2 equals 100. Then we can take moments about, let's say, this point 1. And so we have 100, which is at a distance of 0.25 from the point where R1 acts. So that's 0.25. You can see that the moment due to 100 Newton force is going to be in the clockwise direction, so negative sign. Then we have R2, which is a distance of 1 meter, and that produces a counterclockwise moment, so positive, 0. So from this, we can solve for R2. It comes out to be 25, I think. And then R1 is 100 minus 25, which is 75. Okay, let's proceed and draw the shear force and bending moment diagram with this information. Draw the beam again. R1 is 75, 2 is 25, P is 100. These are the lengths. Okay, shear force diagram. Okay, so on the left, we have 75 upwards. So clearly that force is going to be 75. Okay, and then as you reach the point where the 100 Newton force acts, that's going to be downwards. So we need to do 75 minus 100, which is negative 25. It keeps going there till you reach here where there's an upward force of 25. So net will be 0 here. Okay, now let's do the bending moment diagram. Okay, what's helpful here is to find the area under this curve. So it's going to be 75 times 0.25. So it's 1/4 of 75, which is 18.75. And then area under this curve is going to be, I should have put 25 there. So that's going to be 25 times 0.75, which is minus 18.75.
Boom. To 0.
Here with that, we can sort of easily draw the bending moment diagram. So it starts off at 0, and then it varies linearly with distance, because it's going to be something like 75 times x, where x is the distance from the left side. So it'll keep increasing and go up to 18.75, because that's the area under the curve, 18.75. And then you can see on the right side, it decreases by 18.75, ultimately reaching 0. So it'll also be a straight line because the force is concentrated. It's okay. So what we observe here is that the maximum bending moment occurs at the point where the 100 Newton force acts, which we know. Now, there's something else going on here, which is there's a discontinuity. Well, there's a change in geometry, right? So right at 0.5 L, we see that the geometry changes. So what we need to do here is we also need to consider the moment at this point where the geometry changes are 0.5 L. So we'll find the moment at 0.5 L, we'll compute the stress at 0.5 L, we'll also compute the stress at point P, where the maximum Mx, and then the larger of the two is the maximum normal stress. So let's do that too. So let's find the stress at 0.5. Okay, so this is 0.25, 0.5. Okay, there are many ways to find the stress at, or sorry, the moment at 0.5. One way to do is to use the similar triangles. This triangle is similar to this big triangle. So we can sort of equate the similar sides. So 18.75 is this side. So 0.75. This is unknown. Let's call that x. And then we know that this side is 0.5, so 0.75, which is also the corresponds to this one. So I put it in the numerator. And then this smaller side, which is from here to here, is 0.5. So 0.5. So solving for x, we have 12.5. So this is 12.5. Okay. So we have two candidates. As I said, this is one candidate where the stress will be maximum, and that's because the moment is maximum. Here's another candidate where the stress could be maximum, and that's because not because the moment is maximum, but because there's a stress concentration, there's a change in geometry. So let's compute stress at both those points. So let's call this point as.
So that second one, like stress. So A there is the max, like stress.
No, that's the moment.
Yeah, A is max moment, and the max stress is going to be at that 1.5L.
We don't know right now. So that's what I'm saying. We need to compute the stress at A and at 0.5L, and then the maximum will be the normal stress. So let's just do that. Let's compute sigma at A and 0.5L. And okay, let's do that. So the easier one is at A, right? Because it's simply sigma at A is m y divided by I. M is 18.75. Y is the distance from the neutral axis. So this is the neutral axis. So if you see this cross section, this is for A. That's capital D. And half of that is D divided by 2. So this is the neutral axis. So, and also we're given the thickness. So thickness, the thickness is this. So I'll draw that here. So we have capital D and T. So Y is D divided by 2 because the neutral axis is this. The inertia is 1/12 B times H cube. B is T, and then the H cube is D. So I'm going to sub in the value for D. I think I gave D as 1.1 centimeters, and then T is 0.1. So let's use that. So that's meters now divided by 2. 1/12 thickness is 0.1 times 10 raised to negative 2. T is 1.1 times 10 raised to negative 2 cube. Okay. Solving for sigma A gives me 929 MPa. Okay, so let's keep that aside for a moment. Okay. Let's now compute the stress at 0.5L where the geometry changes. So I need to pull out the stress concentration factors for that. So let's let's find cert picture. Okay, this is the geometry, right? And what I need is to find the stress concentration factor. I need two ratios. One is capital D divided by small d. So capital D is 1.1. Small d is 1. So this is 1.1. Small r divided by d. So small r is 0.1. Small d is 1. So it's 0.1. So let's locate. So 1.1 is right here. So we're looking at this curve. And then we need to compute 0. We need to find where 0.1 is, which is here. So it's this. Okay, so it's conveniently at 1.6, right? Okay, so with that, let's compute the stress as 0.5 L. It's going to be M Y divided by I. And now let's look at the geometry there. So we have at, this would be, now we're finding the stress here. Right, so we're looking at not the larger diameter, but the shorter diameter, because that's where the stress is higher. Smaller the diameter, the higher the stress, because they're inversely proportional. So let's go and draw that first. That's small d, and that's the thickness. And I forgot to put here stress concentration. So it's going to be stress concentration times M times Y divided by I. Okay, so let's put in the value. KT is 1.6. The moment we found earlier, it's 12.7. It's 12.5, right? So let's put 12.5. Y is small d divided by 2. And I is 1/12 B, which is T, times D cube. So let's sub that in. 12.5. Small d is 1 centimeter. So 1 times 10 raised to negative 2 divided by 2 divided by 1/12. Thickness is 0.1 times 10 raised to negative 2, convert into meters. And then D is 1 times 10 raised to negative 2 cube. So doing this computation, we have, what I got was 1200 MPa. Okay, so if you go back and check the stress, at A, it's 929, but the stress at 0.5 L, where there's a change in geometry, it's 1200 MPa. So that's the critical point. So this is the maximum normal stress, which is at x equals 0.5 L from the left. Okay, so here's an example illustrating how stress concentration changes the location of the maximum stress because of KT. Yes, I think I have time for one more. Any questions? This is a simpler one. So this is an element where there is normal stress of 30 in both directions, and then the shear stress of 25. We need to compute the factor of safety, assuming shear stress theory and distortion energy theory. So what we do first is identify the stresses. Sigma x is sigma y is 30, and tau xy is 25. And the next part is to identify the principal stresses, which is a formula which will be given to you. It's sigma x plus sigma y divided by 2 plus or minus square plus. Okay. You could also get the principal stress using Moore's circle. Now it's not asked, you're not asked to draw the Moore circle, so you may as well use any method you choose. So you have 30 plus 30 divided by 2 plus or minus 30 minus 30 square plus 5 square. So from that, you can pick one for sigma A, pick one for sigma B. So it actually comes out to be 30 plus or minus 25. So one of the stress is 30 plus 25, which is 55. Okay, the other one is 30 minus 25, which is 5. And then that's about it. Right, those are the principal stresses. Now, what you want to remember is when you're using factor of safety, you're looking at 3D stresses. So the third stress is 0, right? It's the stress in the Z direction, principal stress. There's no stress in the Z direction. So it's sigma C is 0. So then when you want to apply these theories, let's do part 1. You want to find a factor of safety using the maximum shear stress theory. So that says that the factor of safety is Sy divided by 2 divided by sigma 1 minus sigma 3 split tau max. Okay. So Sy divided by 2, tau max is sigma 1 minus sigma 3 divided by 2. Effectively, this is Sy divided by sigma 1 minus sigma 3. So what are sigma 1 and sigma 3? Sigma 1 and sigma 3 are the principal stresses such that sigma 1 is the maximum stress and sigma 3 is the minimum stress. So from here, we can identify what these are. So sigma 1 is the maximum of all three, which is 55. Sigma 2 is the middle one, which is 5. And the sigma 3 is 0, which is sigma C, which is 0. So the factor of safety now is going to be 65 divided by 55 minus 0, which is 1.18. Okay, it's important to note that 5 does not appear in the equation because that's not the minimum stress. So for part 2, we need to use the distortion energy theory. And that one is kind of straightforward. It says that N is Sy divided by the von Mises stress, which is sigma A square plus sigma B square minus sigma A sigma B, 65 divided by 55 square plus 5 square minus 55 times 5. That's 1.23. So that's the answer. Okay, so the distortion energy here is kind of straightforward, but note the maximum shear stress. You always want to number them down in the descending order, sigma 1, sigma 2, sigma 3, before you use that in the equation. This was not the case in the term 3 problem, where sigma 3 happened to be sigma B because sigma B was negative, so it was the lowest stress. Okay, so I think we have time for one more. Any questions on this? That's straightforward, right? Okay, so here's a similar problem, but this one is on a different theory. Given SUT and SUC using modified Moore criterion for ductile materials, estimate if failure will occur or not. So this one asking, will failure occur or not? Okay, so when will failure occur? Well, it will occur when the factor of safety is less than 1. That's one way. The other way is you can use that equation and see if that left-hand side equals 1 or not. So the one I like to use is this one. 1 divided by n equals sigma 1 divided by SUT minus sigma 3 SUC, and if n is less than 1, failure will occur. That's just saying that the maximum stress will be exceeded. Okay, so let's try to find n then. Right? That's the whole point. SUT, SUC is given. So what we need to do is now find the maximum stresses, sigma 1 and sigma 3. So sigma x is minus 32. Sigma y is 0. It's not there. And tau xy is 75. So sigma a comma b is, using the same formula I wrote down earlier, it is minus 32 plus 0 divided by 2. That's sigma x plus sigma y divided by 2, plus or minus sigma x minus sigma y square. So sigma x minus 0 by 2 square plus a tau xy square. Okay, so that comes out to be two values. One is 60.69 and minus 92.69. So in other words, sigma A is 60.69, sigma B is minus 92.69. Then there's a third one, which is clearly 0 because it's a plane stress. Now we need to arrange them in ascending order. So maximum stress is 60.69. The next one is the next lower one, which is 0. And then the last one, which is the minimum stress, is minus 92.69. So all I need to do now is use the equation equals sigma 1, 60.69 divided by SUT, which is 80, minus 92.69 divided by 200. Okay, when you crunch the numbers, it comes out to be 1.22. But remember, that is 1 divided by n. To find n, we need to take the reciprocal of 1.22. N comes out to be 1 divided by 1.22, which is 0.81, 0.82, which is clearly less than 1. And then you can predict that failure will occur. Okay, so that's the